What we're going to be going over here is the directional derivative here, and we'll do it in terms of the production function. And the production function we're going to be looking at is going to be similar to the Cobb-Douglas production function. Okay, so this is going to be our production function here. We're going to have our profit. It's going to equal some revenue here less our costs. So the production function we're going to be dealing with is here. So we're going to have output here would be profit as Q here. And then our revenue would be, in this case, we're going to be just looking at $1,400 here per unit for each product we sell. And we take that revenue, or our units parameter here, times our material input and our labor input. And each of those are raised to some exponential amount here. And really that's the share of the output here. Material is going to represent approximately, what, 0.5035 here, the exponent amount. That's about 53 or 50.3% here of the revenue. And our labor here is going to be raised to 0.3215. And that represents about 32% of the revenue here. And then we'd also have the cost on a per unit basis here for material and labor. But we're not going to include it in our analysis here. All we're going to be looking at is the revenue portion here to our production function. And what we want to get down to is we want to determine what they call the directional derivative here based on our inputs here and our units parameter, or our units sales price, in this case, that for each unit we're going to be selling. And really this directional derivative is really looking at the change in output here at some point on our production function, on our function here. Okay, so just looking at it in 3D here, I have it laid out just to get an understanding of what we're going to go through here. We got some material inputs and some labor inputs showing down here. And then based on those inputs and that production function we have here showing up here, this is what we're going to get as our surface plot here for our production function based on a sales price or a revenue per unit that we're selling here at $1,400. And when you're dealing with your directional derivative here, you got to have some targeted outputs. And in this case, we're going to have some targeted outputs, and I've calculated these where we had some constraints here for our material and labor. And our targeted output in this case, we came up with 70 here in units of material and 78 here units in labor, and we come up with targeted output. We got 48,144. So this is what we're going to be working with. Okay, so let's go and take a view of it up over here. Okay, so we're going to first look at do some definitions here visually so you get some understanding of what we're going to be doing here. So first look at our targeted line or plane here, and really that's going to be the slope of the directional derivative here. And I got that, our targeted output I'm showing here, and I got that surface plot here for our function here. So that's our output function we have here. Plotted it out here in a surface plot. So what we're going to do first for our slope or of our directional derivative is really what we have to do based on this targeted output. We're going to have some tangent line or plane here. I'm showing that in green here. And that's going to be the slope of our directional derivative here. And then shown in yellow here, that's going to be a cutting plane. And the idea here is you want to get this cutting plane to go in the same direction as your directional derivative here. And that's where you're going to be maximizing your output, or in this case, the profit here. Okay, so just moving over here, getting the other thing we're going to have is that blue path that we're showing up here, showing that over here all the way up. That's really the gradient path that we're going to be looking at, and that's where we get the path that we follow here to get the maximum output, or in this case, earn the maximum profit here. So we've got our tangent line we looked at here in green, and then we have, again, just to go back with this cutting plane here, I'm showing that in yellow. That's really desired direction of your directional derivative here to get the maximum output here. So again, blue here is our gradient path, and I'm showing it here. I've got a wire framed here, or you can see-through here for your production function. So you can get a little better idea here of what we're talking about with this cutting plane here and our tangent line or a plane that we're going to be looking at. Okay, so that's visually here looking at the cutting plane and our tangent line. So if we move down over here, just by definition, the directional derivative really measures the marginal change in output when inputs, in this case our material and labor, are changed marginally in some ratio here. So much material to so much labor here. So that's what we're going to be looking at here. So if we go down here and just look at it from the underside of that production function here, just to get a little bit idea. Remember, Q here, our profit is shown on a vertical axis, and then we got our labor and material inputs shown down here on our horizontal axis. So we're going to have some, just to get an understanding, again, when you're dealing with the directional derivatives, you have to have some targeted output. In this case here, remember that our targeted output I showed up here. Well, this is the underside of our profit function. So this elevation here, this vertical increase here from zero profit here up to, in this case, that was 48,000, excuse me, approximately here. That's going to be what we refer to as our targeted output here. Okay, and then if we move over here, well, let's first maybe make some definitions here. The directional derivative and the gradient vectors here are our marginal output. Really, those are the tangent paths for our material. We're going to be looking at gradient vectors, we're looking at the tangent plane, and we're going to be looking at the marginal product here, and those are going to be the tangent paths for our material and labor here. So this, our definition to understand what's going on. These yellow paths that I'm showing here, there's our tangent path for our marginal labor and material here. Labor would be shown over here, and material shown here at a certain targeted output that we're going to be looking at. And then we get up to the point here where we have our targeted output. This is where we're going to be looking at our directional derivative here. This red arrow showing up here, and that's really split between the portion here for labor here, moving out here, and the portion here for our material here. And then it's sitting on some plane here. I'm showing that as a green plane here. And that plane here is really, the slope of that plane here represents our directional derivative, or the amount of change that we have here in our output based on our inputs here for material and labor here. So this is what we're going to be looking at, and we're going to break this down. The next thing we have to deal with is the gradient vector path, and that's really the direction of the greatest increase here in our output. And we do that through a partial differentiation here of our function. This is where we're going to take the derivative of one of our variables and then keep the other constant. We'll go through that here. Okay, just by definition here, again, this gradient path here, I've shown our production function I've got shown here, graphed out in 3D here. Now the gradient path, that is the path here of our maximum output or production, and that's that red line here. I'm showing at zero or inputs here for M and L, or material and labor here, and as you put more and more material and labor, you want to follow up this gradient path here. Okay, you want to follow that path because that's where you're going to get your maximum output, this red line here. And our target point is shown here. And based on that target point here, I would have come up with the material input here, I think at 70 units, and labor input here at 78 units. So I've got the material shown here and the labor shown here. And based on those inputs here, material and labor, they move up along what they call the tangent path, or the marginal product for each one of those inputs here for material and labor. And those are those yellow lines that I'm showing here. And when they're going to cross here right at my target point, because that's the way I solved this equation here by looking at the maximum output beta based on our constraints. And they pass right through our target point that we have here. Okay, so that's just to get a basic understanding here, marginal output. And the key is here with these yellow or these tangent paths here for your material and labor. You can see here when your first units of material and labor, you got a real steep increase here. You get a lot out of your material and labor, and as you, that is, it produces more to your output here, and based on your production function here. And as you increase the number of units here for each of them, you get less and less output. That's based on our production function here. Okay, so that's our first one that we're going to look at. And then moving over here, so you understand the gradient path and our tangent paths here being our marginal output. So let's move over here, just looking at it in terms of, and this is the case here, I'm looking at different inputs. I'm only going to use 10 units of material here and 10 units of labor. So we got these, my targeted output is still here. But based on those inputs here, material and labor, our marginal output or our tangent lines here don't even make it up to our targeted output. They just veer off here and they move up at the rate here that we're going to be looking at. So this is where you're going to get your marginal output at a different rate here, and we're going to look at that here. Okay, and then the other thing is, just to understand it, our gradient path here, that's this gradient path that you're following up here where you get your maximum output, you're really looking at a proportional increase here in your material and labor here. You got to increase them proportionately here to stay on your path, to get your maximum targeted output with whatever constraints you have here. And then these other lines that I'm showing here, these, they call them level lines here, that I've got them plotted out here on our production function. Those are really the level curves or our equal product lines here, where you get equal product out if you follow those lines along. And really the key is here, the gradient vector here has to be perpendicular to those level lines here to get your greatest increase here. And then again, those yellow lines here, those are tangent paths, and really that's the change in slope in material and labor here is your marginal product here. Okay, so we got a basic understanding of what we're talking about here. So let's go down and let's make our calculations. Okay, again, just remember these key is here, those tangent lines that were these yellow lines here. That's the change in slope here in material and labor. That's how they change regarding the output that you're looking at the particular input here of each of those. Okay, so what you have to do here, you have to come up with a partial derivative here, and you have some fancy equation here, and we'll just basically go through it. But what you want to do here for your plotting and solving all these equations, you want to come up with some software package where it's going to do it for you here. And in this case, I've used MapleSoft here. So let's just get a basic understanding of partial derivative here if you don't understand what it is here. So here's our production function, and let's say we'll take a partial derivative here in terms of x here. So the key is here, we're going to keep our y constant here, our y and the exponential amount here constant, so that just goes down into our partial derivative here. And then our x factor here, or x variable, you just subtract 1 from its exponent here, and that's going to give you, and then you take, well, first off, you take its exponent times the coefficient here of 1400, you're going to get up 704.90. And then 1 from that exponent here is going to give you, it becomes, because it's a negative amount, it becomes down in your denominator here, your exponent, to 1 minus, this minus it is going to give you this degree here. You started out with 50.5035, subtract 1 from it, and you're going to get 0.4965 in the denominator here. And then the same here for the y function. You'd be holding your x constant and just take your y coefficient here. You take your y exponent times the coefficient here, and you get that value, and then minus 1 from it, your y becomes in the denominator here by that amount here, just the difference between this amount and subtracting 1 from it here. But the key is here, what you do, we're going to, based on those partial differentiations, partial derivative here for the f and x, and y here, f of x would be like for material, f of y here would be like for labor here. So what you do is you just put in, at the targeted point we're dealing with, the 70 units here of, I think, material, 78 units here of labor, you plug those into your partial differentiation, you're going to come up with the slope here. So this is really what we want to get down to, the slope here, or the change, the rate of change at that particular point here for your material and labor. So for your material here, I guess x slope would have been 347 here, and for our labor here, I come up with a y slope of 198.85 here, and that's really what you're looking at that particular point of output here. But the key is here, we've gone through the partial differentiation and got an idea of what our output slopes are, how much we're adding to our output at that particular point. But you want to get down to this gradient vector here. So just understand the gradient for our output x here, or our material, that was the slope here, 347.01 here. And then this is a vector. We're going to have to deal with this when we come with our directional derivative. And then we add to it the slope here for our labor here, 198.85 times some constant, or some amount here, some varying amount. So the gradient vector is the key here. All right, so maybe we could go back up and just look at it, that x slope here and our y slope. So if we went back up here to our diagram, our x, I think, was for our material input here, and at this targeted point here, I came up with for our, based on our material, it was a slope here 347.1 here, and then for our labor here, that was our y slope here, 198.85. It's a little hard to see the slope here looking at labor material, but that's what we're talking about at that particular point here. Okay, and now let's go and let's look at our second situation here. So this is the case here where we have our inputs here of labor and material, and just put it at 10 units each. Remember over here we had 70 and 78 units respectively. Here we're just looking at 10 and 10. So you can see, plotting it out here. Incidentally, I'm using MapleSoft for the plotting here, and it gives you an idea of what's actually going on rather than just looking at formulas and numbers and so forth. You get a visual understanding of what's going on when you do that here. So based on those inputs, you can see what's going on here. But what we go down here, and this is what we want to look at here, that rate of change, if we went through, we get the same partial differentiation, but when we plug these numbers into it, we're going to get an x slope here for material at 471.11. And if we went over here to our x slope here based on those 70 and 78 inputs, we get a lesser amount, 347 here. And we can go up and look at that, because you can see here, this is at that 10 units here. So you're going to get that, if you've gone up to your diagram here, you're going to get a real steep amount here. And you do that in both cases here. Those initial amounts here, inputs here, you're going to get a greater increase based on your function here. All right, and if we go down here for tracking back here, if we look at our y slope here based on those inputs of 10 and 10 here, we're going to get up 300.82 here. And just by comparison, where we got these first units at 10 and 10, looking at those first units of input here versus our later units here at 70.78, you can see the difference here in the slope. That's the only point I wanted to make here. First units here, you're going to get greater output here than you do with those more or later units that you have here. 471 here versus 347 for our material input here. And then if we look at our labor input, we're looking at 300.82 versus 198.85 here. And again, understand this gradient vector, because this is the key that we have to work with when we're coming up with our directional derivative. This is why you came up with these amounts here, the change in slope, or in this case it's the marginal product. Gradient vector, the x factor or x slope here becomes first part of our vector here, e 471.11, and then y here, our y slope for our labor here becomes, you add to it, that becomes the next exponent here for our labor, 300.82 here. So the thing is here, this gradient vector, that's the direction of our greatest increase here. And that's what we're going to have to deal with when we're looking at the directional derivative. We want to get both our directional derivatives and our gradients going in the same direction to understand where we're going to get our greatest increases. Okay, so we'll move on. Now we'll calculate our directional derivative, or the vector here at the point that we were looking at here, our target point. And really that's the slope of the tangent plane in the direction of the point, or our target point. Now really that's the rate of change in a specified direction. So that's the key here. You have to have a specified direction and a targeted point here. Really the directional derivative can be the slope here at any point in any direction, but it's meaningless here, the directional derivative or the directional vector here, until you specify a direction. Okay, so going down here and looking at our function here plotted out here, this red arrow here, that's really the directional derivative we're looking at here. And that directional derivative is really composed here of our material input here, and those are those the slope here, or change in our marginal products for our material here and our labor here, those yellow lines, and those are depicted here by the arrows here for, let's say, our material input here and our labor input. Knowing our labor and material input at our targeted point here, whatever those changes are, we can determine our directional derivative here. Okay, so just going back over here, maybe it's a little easier to see here. So on this side here, just looking at our see-through wire diagram here for a production function, our directional derivative is shown here, and then say our labor input here is this vector here, and then our material is the vector here. And those vectors here for your material and labor become your directional derivative. And in our case here, our directional derivative here it is sitting on the gradient path here. And that gradient path, that's the path here of the greatest increase in output here. And then I'm just showing here we had starting here at 0 inputs, and then we moved up here to our targeted point here shown in this blue line. That's really our output. Okay, so what we're going to, again, our target point for our output here was 70 units of material and 78 units of labor here, and that is our specified direction here. And what we're trying to do here, we have to have our, first off, let's look at it. The direction for our, we have to determine our directional derivative here, or the direction of the greatest increase here in our output, and they call that the vector dot product here. So let's just understand how we would calculate that here. So let's look at the case here. Our directional vector here is really those 70 units here of material plus 78 units here of labor. That's this directional vector here, but we have to convert this directional vector here into a unit basis before we can use it and to determine our vector dot product here. So just understanding what that is, we just use the Pythagorean theorem here. We have a right triangle, M and L here for material and labor. So you take whatever your material input here, square it, plus your labor input here, square that, and just take the square root of that quantity here, and you divide it into the unit here for material. I guess our labor here was 78, and you're going to come up with a unit amount here, and you have to have a unit amount, otherwise it doesn't work. So that ratio, or that division here, gives you 0.74428 here, and that would be for our labor. And do the same thing for material here. You just take, again, you take your 70 units plus 78 units here, square those, add them together, take the square root and divide it into the units here for material 70, and you're going to come up with, I think, 0.66794. So we have to convert our directional derivative to a unit length here, and that is the key here. Okay, so let's go over here. Now we can determine our direction here of the greatest increase here, or our directional derivative, based on the fact that we had that target point here on our gradient path with the greatest output. And you take the vector dot product. So let's look at it. So our gradient vector that we calculated earlier was for M here was 347.1, and take times some quantity here, the vector length here, plus 198.85 here for our labor here. Okay, and now we take our directional vector here on a unit basis that we calculated here. For material, I got 0.6679, labor 0.7442. So that's why we had to come up with that unit basis. So you take that times your gradient here, just match up your, in this e to x is here for material, e to y here is for our labor. So you just take the gradient here for your gradient vector here, that's the direction of the greatest increase here, times your unit vector here for, in this case, material, and that's going to give you, that multiplication is going to give you the portion here for material is 231.77, and then for labor, same thing here, just take 198.85 times its unit directional vector of 0.7442, that's going to give you 147.98. So you add those two vector quantities together here, 231 plus 147, you're going to get, this is where you get the directional derivative here. And this is what we were trying to get down to. And that's 379.75 here. So that's really the slope of the plane here, based on our targeted point for our material input here and our labor input. This is what we're increasing here, our output here at that rate here. So we could have gone through all this mechanics that we went through. In this case, I used the MapleSoft. We could have just put in a simple command here, and it would have given us the, based on our function that we have and our inputs, it would have given me a directional derivative here, this amount, 272.92, square root of 2, and that come up with a directional derivative, and that's that slope, or that rate of the greatest change here in our, for our output at 385.96. Okay, compares to what my multiplication is here. I didn't put enough decimal points in here because that's the only difference. 379 versus 385, just didn't carry out enough decimal points. But you have to really have some software package where you can put this all in. It just takes a little bit of doing, and you can come up with your derivatives that way. Okay, so that's our, what they call the vector dot product, if we refer to that, and that just gave us our directional derivative amount. And then just to sum it up here, let's move up over here. Okay, so back to our production function here, looking from the underside. This is the bottom side of that, our directional derivative, or that tangent plane here at that point here. And really that's, again, the directional derivative. You can see here that from the underside, this was 147 point. That was for, I guess, our labor here, plus 237 here for our material. That vector here, that one, add that one, and that one together, and you're going to give our directional derivative here, which is is really a amount here. It's not a vector, it's just amount of increase that we're looking at. In this case, it's an increase in the direction, and actually at that point, 379.75. So that's the change of our slope and material here, and that's what we talk about the directional derivative here. It's really a scalar amount, or it's a quantity here at a targeted direction. And just moving down here, again, just to understand it, looking at it from the top side here at a side profile here. Here's our production function. Here's the slope of that directional derivative. That's really our tangent plane based on our labor and material here. This directional derivative, this red arrow is shown here. Again, looking at and that's at that targeted point here where we had, starting with 0 to our targeted point here for our output here. And I don't know what that was, 44,000 or something in the 40,000s here. But at this point here, we're adding to our output at a rate here of $379 per unit of input here for material and labor. And remember, they have to be put in, I didn't mention it, a proportional or an amount here, that ratio that we looked at here, at that unit vector amount, essentially. We're putting them in at that proportional amount, and this is what we're getting out at exactly at that point that we're looking at. Okay, so that pretty much sums it up here for the directional derivative. It's a long process to go through here just to explain it, but looking at it in terms of these 3D diagrams and our calculations, you get an understanding of what we're talking about.